We'll now discuss the Seidel's algorithm for computing the distance matrix of the graph which is undirected and unweighted, so that the distance matrix D for a graph G is a matrix where for the pair of vertices Vi and Vj, the entry of the matrix corresponds to the distance between Vi and Vj. To compute this matrix, we would cleverly use squarings of the modified adjacency matrix, which we have considered in the previous algorithm. But first, we'll need to talk about the lengths of paths and distances in the original graph G and in the square of G. So if the original graph G is an undirected graph with vertex set V and edge set E, then G squared is a graph with the same vertex set and the edge set as follows. So here we have an edge from U to V in the square of graph G for all such pairs UV such that U and V were originally adjacent in the graph G, or there existed an intermediate vertex that linked U and V. That is, if the distance between the vertices U and V, which we'll denote by D sub G of U and V, was exactly equal to 2. So now, let's compare distances between the same pairs of vertices in the graph G and in the square of G. So let's take our graph G and any pair of vertices and the corresponding path between these vertices that has the minimal length, so just the minimal number of edges on this path. This is a path that has length exactly d sub g of uv. Now, if we look at these vertices on the path, they are linked by an intermediate vertex. So in g squared, there will be edges like this, and like this, and like this, and like this. So we'll have a lot of edges in g squared, which we didn't have in g. Well, all the edges of G are naturally also the edges of G squared because of this property. So now we can see that if the original path was of length, say, 2k plus 1, like here on the picture, we have a path of length 5. Then each pair of vertices on this path, consecutive pair of vertices, has a direct edge between them in G squared. Thus, the distance between the same pair of vertices in the graph G squared would be equal to k plus 1. So they say that in case when the distance between U and V was odd, the distance in the graph G between the same pair of vertices would not exceed k plus 1. But now, what if the distance between U and V in G was even? What if we had, say, 2k here? Then we would have this picture in G squared, and the distance according to the graph G squared between the same pair of vertices would not exceed k. So we see that in both cases, the distance between the pair of vertices in G squared does not exceed the ceiling function of the distance between the same pair of vertices in graph G divided by 2. And actually we can prove the opposite inequality as well. So if we now look at the distance in graph G squared between our pair of vertices UV, so let's take the same pair U and V, but now let's concentrate firstly on the shortest path in graph G squared between them. So we have some edges on this path. Now each of these edges correspond either to a single edge of graph G, or it corresponds to some path of length 2 in between these vertices, so that we immediately see that there exists a path of length at most twice the red path. So this allows us to write down an inequality for distances in graph G bounded by twice the distance between the same pair of vertices in graph G squared. So now if we plug this bound in here, what we get is the continuation of the chain of inequalities like this. So dg of uv can be bounded by 2 times g square distance between u and v over 2, And that's exactly the same thing that stands at the left part of the inequality. So this chain of inequalities essentially gives us the equality in all these places. So now we know that actually we have equality here, and we'll proceed with this knowledge. So this equality gives us that dg of uv is equal to either dg squared of uv times 2 or the same thing minus 1. And let's now devise a quick way to actually check which of these two cases takes place. Now it turns out that we have pretty deterministic picture, but still, well, not quite determined because we have two cases instead of one. So how do we distinguish between these two cases? Can we reconstruct the distances in G knowing the distances in G squared? And it turns out that we can do it, again with help of matrix multiplication, but to explain this we first need the following lemma. So this lemma tells us how to distinguish between the cases. In case when the distance in G is exactly twice the distance in G squared, for every neighbor of vertex V, we have the distance from U to the neighbor greater or equal than the distance from U to the vertex V. And if we have this case happening for distance between U and V, then firstly, for every neighbor, we have the opposite kind of inequality. And moreover, there exists a neighbor for which we have a strict inequality here. So let's prove the lemma. We have the distance in G twice the distance in G squared if the picture is like this. So we have U and V, and in G squared we have a path between U and V, and each of these edges corresponds to a path of length 2 in G. So now if we take an arbitrary neighbor of vertex V in graph G, that's W, if we assume that there is a shorter path in G squared between U and W, like this, then we see that the shortest path in G between U and V can actually be made smaller than we have assumed. We have assumed that the shortest path contains 6 edges, whereas this path would have just 5 of them. So indeed, in the case when the distance between U and V is an even number, we have these inequalities. Now let's consider the second case, this one. So we can have this odd number here if one of the edges of G squared corresponds actually to a direct connection in G between some pair of vertices. So the picture is like this. And then we see that this vertex, which is actually a neighbor of vertex V in G, which we can now denote by W prime, satisfies this property. The distance to it in G squared is less than the distance to V. And whatever other vertex neighboring V we take in G, as we have these two edges in G, then in G squared we have a direct connection like this, and thus the distance between U and W does not exceed the distance between U and V. So this is a sketch of the proof. Of course, you might want to consider a case when, say, this edge, which is close to V in G squared, actually corresponds to a path of length 2, and say this intermediate edge corresponds to a direct connection in G, but this case is analogously considered.